Hello everyone, Kotumane, the Naked God here. Um, Let us have a look at a problem that will help us get an idea as to how we approach problems based on laminas. All right. Now, let's consider this lamina on figure 3.9. Right. Problem statement reads calculate the magnitude and direction of the unknown forces in figure 3.9 when the forces keep the lamina in equilibrium. Right, when the forces keep the lamina in equilibrium. Right, the forces are coplanar. Take P and Q as upward forces. So that means that's going in that direction, and force Q is going in that direction. Right, we've been told to take these forces as upward forces. Right, now we've been told here that the forces acting on this lamina are keeping the lamina in equilibrium. All right, hence we know in applying conditions of equilibrium, right, the conditions of equilibrium must be such that they are both equal to zero. So meaning that in applying conditions of equilibrium, in calculating forces P and Q, right, in calculating forces P and Q and applying conditions of equilibrium, that's equal to zero, and the sum of forces in the y direction also equal to zero. How do we know this? Because we've been told that the forces, right, are keeping the lamina in equilibrium. So this scenario in particular, we know that this is equal to zero, right, and this is equal to zero. Right, now as you should know by now that in applying these conditions of equilibrium, we are only able to use forces that will be, right, for this condition of equilibrium, that will be we'll be able to use forces that are parallel with the x-axis, and then when applying this condition of equilibrium, we'll only be able to use forces that are parallel with the y-axis. Right, now here you have this force, the 400 Newton force, which is parallel with the y-axis. Right, then force P and Q, right, are neither parallel with the x-axis nor the y-axis. Hence, right, we take it as being oblique forces, saying that they're acting at an angle, right, with essentially the axis. Right, now this one in particular, force P, is acting at an angle of 30 degrees from the x-axis, right, and then Q is acting at an angle of 50 degrees from the x-axis. Right, remember I said it is preferable that you reference your forces from, not your forces, you reference your angles from the x-axis. Right, so seeing that both these forces have been referenced from the x-axis, right, or the angle thereof, we will use the angles as they are. This helps, right, in keeping the components, right, to be expressed. For instance, the horizontal components will be expressed in terms of cos, and the vertical component will be expressed in terms of sine. Why? Because the angle we are using is a reference from the x-axis. So that is to say, all right, looking at the components of P, right, if P is acting in this direction, it means it is in the first quadrant, right? So because it is in the first quadrant, it means its components, making sure that the direction thereof, right, goes towards, right, the direction of force P. It means the vertical component will be in this direction, and seeing that it is headed up, it is positive P sine 30 degrees, and then the horizontal component is headed east, so it's positive P cos 30 degrees, right? And then we're looking at Q. With Q, you're going to have, let's create some space here, put this here. So here you'll have the vertical component headed in that direction and the horizontal component headed in that direction, right? The component of Q in the y direction, all right, will be, it's headed upward, so it's going to be Q sine 50. And then the component of Q in the x direction will be, seeing that this one is headed west, or is headed in the negative x direction, we're going to take it as negative Q cos 50. All right, if you look at our horizontal components, both of them are in terms of cos, and if you look at the vertical components, both of them are in terms of sine, right? The reason why that is so is because the angle we have used, so the 30 degrees for this oblique force is a reference from the x-axis, and with this one, all right, the angle is also a reference from the x-axis. Right, so seeing that we've resolved our oblique forces into its components, now we have forces that are parallel with the x-axis and the y-axis, hence we'll be able to apply conditions of equilibrium. All right, first looking at the sum of forces in the x direction. All right, forces in the x direction, we have positive P cos 30 plus, all right, then the horizontal component of the Q is negative Q sine 50. All right, there's no other force in the horizontal direction is equal to 0. All right, and then if you punch cos 30 in your calculators, you're going to get 0.866 P. All right, and then of course this becomes negative, and then sine 50 is 0.643 Q is equal to 0. All right, now we have two unknowns here. Right, having two unknowns means that you require two equations. Right, if you have two unknowns requires two equations, which will then be solved simultaneously to solve for what you are looking for. Right, so if you have the number of unknowns tells you of the number of equations that you are going to need to solve the problem. Right, so formulating our first equation here, seeing that we only have two terms, right, it means you can express one of these, either P or Q, in terms of the other one. Right, so expressing P in terms of Q, right, we're going to take this term and transpose it to that side. It becomes positive, hence you'll have this is equal to 0.643 Q. Right, and then expressing Q in terms of, expressing P in terms of Q, you make P the subject of the formula by dividing both sides by 0.866, thus making P the subject of the formula, hence P is equal to this here. Right, and then if you punch this in your calculators, you're going to get 0.742 Q. So if you say 0.643 divided by 0.866, right, this is what you get if you round up to 3 decimal places. Right, and then this becomes our first equation. Right, so of the two equations that we need, we already have the first one. To get the second one, now we use the second condition of equilibrium that is applicable here, which is this one. Sum of forces in the y direction is equal to 0. Sum of forces in the y direction, right, we have the force 400 newtons. It is headed south, so we are going to take that one as negative. Right, so you have P sine 30, it's headed upward, positive P sine 30 plus, then Q is also headed upward, so it's positive Q sine 50 plus the 400 headed downward, which is negative 400, is equal to 0. Right? Now, if you punch these in your calculators, we are going to get, right, sine 30 is 0,5. So this essentially will be 0,5 times p plus sine 50, right? That is 0,766 times q, then minus the 400, which is equal to 0. Right? So essentially this becomes the second equation. Right? So we have two equations, we have two unknowns, and now we have two equations. Now we're going to solve them simultaneously. Right? By substituting the first one into the second one. Right? So this is essentially the second equation. Now you're going to substitute the first equation into the second equation, right? So this becomes 0,5 into p. P is 0,742 q, right, plus 0,766 q minus 400. Right, now the minus 400 at this point, right, you can realize that these two terms are like terms, right? So grouping like terms, essentially you can take this or you can transpose it to the other side, and then when you transpose the negative 400, it becomes positive 400, right? Now this term plus this term gives us 1,137 q. That's equal to 400, right? And then solving for q, seeing that q is the only unknown here now, you then divide both sides by 1,137, right, making q the subject of the formula. Right, that cancels, and this here gives us the value of q. So 400 divided by 1,137. Right, punching that in your calculators, you should get 351,803 newtons. Right, remember the one force that was given is expressed in newtons, meaning that this force is also in newtons. Right, had the 400 been in kilonewtons, then our answer would also be in kilonewtons. Right, that is just for interest sake. Right, so q is equal to this in magnitude, right, and then p, from the first equation we know p is equal to 0,742 q. So this 742, and then q is 351,803. If you punch this in your calculators, you're going to get 261,038 newtons. All right, and that is how you would approach such a problem. All right. Right. Now let's look at the second problem. Alright, so let's look at the second problem. Right, this here is a lever system, right, which based on figure 3.16, right, you have a force P acting at this point, and you have another force 80 newtons acting at this point. Both forces are oblique forces. Right, now O, the point O is our hinge point. Right, this is where this lever system is being supported. Right, so if you look at the question, the problem statement, calculate the magnitude of force P and the magnitude and direction of the reaction force at the turning point O of the lever shown in this diagram, the system is in equilibrium. Right, so we've been told that the system is in equilibrium, meaning that the sum of forces in the x direction is equal to 0, sum of forces in the y direction is equal to 0. Also, if you are able to use moments, right, because this here is a lever system, right, lever systems we are able to take as essentially beams, right. If you can look at this as a beam which is supported at point O, right, and having forces being applied, right, on this end and on this end. Right, so because we have two forces acting on the lever, right, the hinge point of this lever is point O, right. It means we are going to have a reaction force at this point, right, where this lever is hinged. Right, we're going to have a reaction force at this point. And bearing in mind that that reaction force is supporting oblique forces only, right, it means the reaction force at this point, right, the fact that the lever system or the forces being applied on this lever system are oblique forces suggests that the reaction force at point O will also be an oblique force. Right, will also be an oblique force. Right, meaningly this oblique force is going to have components in the x direction and components in the y direction. Right, now as far as if the components of this reaction force will be headed east or west in terms of the horizontal component, or south or north in terms of the vertical component, right, we have no idea at this point. The calculations, right, having applied conditions of equilibrium, will tell us the direction of the two components. Right, once you've calculated the two components applying conditions of equilibrium, right, we'll then be able to calculate the reaction force at this point, right, using Pythagoras. Right, remember the question is to calculate the force P and the magnitude and direction of the reaction force. Right, this is where this lever system is hinged, so the reaction force will be at this point. Right, all of this, right, is to highlight how we look at such problems. Right, by the time you get to your solution, you've already analyzed, right, the forces acting on the lever system, and based on those forces, right, you look at what these forces or how they are acting, right, you look at how the forces are acting and decide what they suggest in terms of what we can expect here on the reaction force, right. And like I said, because both forces are oblique, it means the support, right, or the reaction force here at point O, right, having to support the two oblique forces suggests that it is also oblique. Right, now luckily for us, there's only one hinge point here, right, which is this one here, right. So because essentially we have two unknowns, we have this unknown P and we have the unknown at the reaction force. Right, so to eliminate one of these unknowns, right, we take moments about O so that we'll be able to calculate the force P. Right, so we take moments about O. Right, we take moments about O, right? And then we apply conditions of equilibrium using moments. The sum of clockwise moments is equal to the sum of anti-clockwise moments, right? That's one of the conditions of equilibrium, right? Or more specifically, static equilibrium. Right? Now, obviously, because we have oblique forces, we need to resolve these into its components. Let's use this. So this will have a component and this x component, right? The y component, right, is positive p sine 45, right? We are able to express the vertical component in terms of sine because the angle we are using is a reference from the x-axis, right? And then the horizontal component is in terms of cos, positive cos because it's headed east. So this becomes p cos 45, right? And then here you'll have this component and this component, right? So the physical component of the 80 newtons is positive because it's headed north, so positive 80 sine 60. The horizontal component is headed west, so it becomes negative 80 cos 60, right? So same applies here. We're able to express the horizontal component in terms of cos and the vertical component in terms of sine because the angle we are using is a reference from the x-axis, right? I cannot express how important it is that you stick with referencing your angles from the x-axis enough, right? I cannot express that enough, how important that is, right? So meaningly, had we been given the angle, so say this is what we are given here, right? So that you get what I mean, right? Say, so that's the y-axis. Say we were given this angle. That angle is obviously 30 degrees, right? Had we been given the angle that is referenced from the y-axis, right, you would work out this angle. Working out this angle, right, obviously that's 90 degrees. So 90 minus 30 gives us that 60 degrees. So even if you've been given the angle that is referenced from the y-axis, always work out the one that is referenced from the x-axis. So that is what I mean by I cannot express how important, right? I cannot express that enough, how important it is, right, to always reference your angles or make use of the angles that are referenced from the x-axis, right? So we've resolved these two components. Now we'll be able to apply conditions of equilibrium, right? Now in terms of moments, we are taking moments about O. Now we are going to look at the turning effects that each of these forces has towards the point we are taking moments about, right? Meaningly, if you look at this upward force, right, you look at the turning effect that this force would have, right, towards point O, right? So if this force was applied, right, was applied at this point, remember, force P is being applied at this point, right? Now we have resolved it into its components, right? Both of its components are essentially acting at this point. So now we look at the turning effect, for instance, that the vertical component would have towards point P. If this was applied at that point, right? So if P sine 45 is at that point, what turning effect would it have towards point O? Right? Obviously, this would have a turning effect that goes in this direction, right? And this direction is clockwise, right? So moments, right, either have a clockwise or anti-clockwise turning effect, and this one would have a clockwise turning effect. The fact that it's headed upward right? This is the effect it will have towards point P, right? This is a clockwise turning effect, right? So this has a clockwise turning effect, right? Clockwise turning effect. And then if you look at the horizontal component, the horizontal component is also acting, right, at this point. Now, if you look at the horizontal component, because we are taking moments about O, right, everything, right, every force that is parallel with the line of action, right, of point O, right, is essentially going to be neglected. Right, so all forces that are parallel, right, with this line of action, right, so meaningly all horizontal forces, right, won't have an applicable turning effect towards point O, right? So this essentially we can ignore. And now we look at force P, right? With force P, its vertical component is essentially acting at that point. So now you consider the turning effects that it has towards point O. Now, if this is being applied here, it means it has this kind of turning effect, right? This turning effect is anti-clockwise. So we say that this one is anti-clockwise, right? That's the vertical component of force 80 newtons, right? Its horizontal component is acting in that direction, right? It is parallel with the line of action, right, of the hinge point O. So meaning that it has no applicable turning effect towards point P, right? So this we can ignore as well. So essentially, we have two moments, if you will, right? One based on the vertical component of force P, and one that is based on the vertical component of force 80 newtons, right? So clockwise moments is the P sine 45, right? A moment is a force times distance. So the distance from where the vertical component is essentially acting to where we are taking moments about, which is 50. So the P sine 45 is the force times the perpendicular distance, which is 50, right? That's the only clockwise moment, right? And then the anti-clockwise moment, right, is the 80 sine. The 80 sine 60, that's the force. The distance from this vertical component to where we are taking moments about is 90. So times 90, right? Now this is what we have here, right? So now we are looking for force P, right? So this can also be expressed as P times 50 sine 45 is equal to, this remains the same, right? So to get the force P, seeing that it's the only unknown here, you simply divide both sides, right? To make P the subject of the formula, we divide by 50 sine 45. And then obviously it cancels this side. Therefore, meaning P is equal to this. And then if you punch this in your calculators, you are going to get 176,363 newtons. Right? Right, so this gives us the value of P. Right, this gives us the value of P. Right, so we have answered the question partially. Now we have to get the magnitude and direction of the reaction force, which at this point we have established that the information we have suggests that this direction force here will be an oblique one, meaning that this will have components as well. Right, the direction force is going to have components. Right, now at this point, if you look at the two vertical components of the two forces, right, they are both headed upward. Right, so meaningly, for the vertical component of the reaction force, it has to support, right, it has to mitigate, right, the two forces heading upward. Right, so for this reaction force to mitigate that, right, its vertical component must be heading downward. Right, so that is just based on looking at how the forces are acting, right, how the two forces are acting. Right, both the vertical components are headed upward. Right, so for this to remain in equilibrium, there has to be a force that counteracts the two forces acting upward. Right, and that force will be on the reaction force. Right, and that force will be the vertical component of the reaction force. Right, that is just based on understanding equilibrium. Right, remember with equilibrium, sum of forces going up must be equal to sum of forces going down. Right, hence the sum of forces in the y direction, right, is equal to 0. Right, so based on what we've just established, we know that there is, call this r in the y direction. Right, the reaction for, or the vertical component of the reaction force is heading downward. Right, so meaning here, in applying conditions of equilibrium, right, you can simply say sum of forces going up is equal to the sum of forces going down. Right, forces going up, right, forces going up is this P sine 45 and this AT sine 60. Now P is 176,363 sine 45. Right, the force that's going up is P sine 45, and the value of P is this one here. Right, plus the 80 sine 60 is equal to the force going down, which is the reaction force in the y direction. Right, so maybe let's call this RO for context, seeing that the point where the reaction force is O. So we can call this RO in the y direction. Right, and then of course if you add this up, right, we get 193,990 newtons. Right, and then of course we have deduced that this is headed south. Right, another way you could have done this, right, had we not thought about it from a practical perspective, right, we could have just said, so let me say, or sum of forces in the y direction is equal to 0. Right, we know this because we know the system is in equilibrium. Right, and then forces going up you take as being positive, of course. Right, and then had we taken this approach, not thinking about the direction of RO, right, we are going to assume that RO is also positive, headed upward. Then the calculation will tell you if the assumption is correct or not. So this would have been positive 176,363 sine 45. We know this one is headed upward, hence positive. This one is also headed upward, so it's positive. Right, and then we say plus the vertical component of the reaction force is equal to 0. Right, so taking this approach, right, not thinking about or not looking at this from a practical perspective, so taking everything as being positive, right? And then this would have been equal to 193,00, 193,990 newtons plus this component is equal to 0. And then of course you'd have to take this to that side, and then RO would be equal to negative 193,990. Right, the negative tells us of this one's direction. So seeing that this is negative, it means that this is 193,990 newtons. Right, this is a y component. This is along the vertical plane. So if it's negative, it means it is headed south. So either way, you get the same thing, right? Regardless of the approach. Right, the practical approach saves times though, right? It saves a lot of time, because from this, based on how these two forces are acting, because both of them are headed upward, it means to be able to keep the system in equilibrium, right? The vertical component of the reaction force has to be acting downward here, right? It saves a lot of time. Either way though, whichever approach you take, you get the same thing, right? So we have the vertical component of the reaction force. Right, now we need to get the horizontal component of the reaction force, and then apply the Pythagoras theorem to get the actual reaction force. Right, so here we now look at, we again apply conditions of equilibrium. Right, the simplest one that we can apply here is the sum of forces in the x direction is equal to 0. Right, whichever condition of equilibrium that you apply at this point, right, will essentially give you the same thing, but this is the approach I am going to take. Right, sum of forces in the y direction. Now at this point, right, we can simply add the reactions, the forces acting in the x direction, or forces that are parallel with the x-axis. Right, we know we are going to have RO in the x direction, right? And then this one is headed east, so it's positive, right? It's positive P cos. P is 176,363 cos 45, right? And then this one is headed west, so it's negative, so minus 80 cos 60 is equal to 0. Right, and then now, because this is what we're looking for, right, you take these two to that side, right, or you can say first that's ROX, and then punch this in your calculators. You should get positive 84,707 is equal to 0. Right, and then you transpose this to that side, and this gives us the magnitude of RO, right, the horizontal component of the reaction force, which is negative 84,0707. It's negative, which tells us the direction. So this is actually 84,707 newtons. And because it is negative and in the x direction, that means it is headed west. All right, which means here that the horizontal component of the reaction force is headed in that direction. This is RO in the X direction, right? Which means the reaction force will be in this direction, right? Now this suggests that if the reaction force is in this direction, it means it is in the third quadrant, right? But we can already tell based on the direction of the components. Where's this thing? So here, this was supposed to be like that. ROI is equal to this, right? So based on the direction of components, what did I do here? Oh no. Oh yes. Yes. Right, so based on the direction of our components, right, the Y component is south, the X component is west, right? Virtue of those two directions, we already expected that the reaction force would be in the third quadrant, right? And then this confirms it as well, right? And then to calculate your reaction force, you now use Pythagoras. So your reaction force will be equal to RO in the X direction squared plus RO in the Y direction squared, right? So this is equal to, now you substitute. Right, substituting RO in the X direction is 84,707 squared plus RO in the Y direction, which is 193,990 squared. All of this is under square root. And then if you punch this in your calculators, you should get to 11,678 newtons, right? This gives us the magnitude of the reaction force, right? To pinpoint the direction, we have to calculate the angle in which it is acting, right? We already know that it is in the third quadrant. That has already been established. But to pinpoint exactly where it is acting, we need to calculate the angle. Right, calculating the angle, right, we calculate this angle, call that theta, the angle reference from the x-axis. So calculating or referencing our angle from the x-axis, that means using tan theta is equal to the y component, so RO in the y direction, divided by the x component, so RO in the x direction. All right, so to get theta, this will be arctan of this. All right, so now you substitute. So arctan, the y component is 193,990 divided by 84,707. Right, and this gives us the angle reference from the x-axis. So this will be equal to 66,411 degrees. Right, therefore meaning the reaction force, the magnitude is 211,678 newtons. The direction, now in terms of direction, right, you should know by now that the direction will be based on, or how you write down your direction will be based on where you referenced this angle from. Right, so because we used this formula, it means our angle is a reference from the x-axis. As far as the x-axis, right, you look at the x component is headed west, so meaning that our direction of the reaction force is west. The angle is 66,411 degrees, headed south. Right. Now, had you reference your angle from the y-axis, right? Had you reference your angle from the y-axis, right? Remember, the angle from your y-axis essentially will be 90 minus the 66,411. So you would have gotten 211,678 newtons. And then if you say 90 minus this, which essentially gives you the angle that is referenced from the y-axis. The y-axis is referenced from south, so your direction would be south. 90 minus 66,411 gives us 23,589 degrees, headed west. Right, so both of these are correct. Right, you don't need to write both of them though. Right, like I always say, stick with referencing your angles from the x-axis. Right, hopefully this was helpful to you. All right, stay tuned for more content on engineering science N3. Right, this is how we approach problems on laminas, right, or lever systems. Right, in the next video we are going to look at how we approach problems based on coplanar and concurrent forces. Right, so remember, laminas and lever systems, right, including beams. Right, the forces are coplanar, but they aren't concurrent. Why? They aren't acting on the same point at the same time. Right, so laminas, lever systems, beams, right, those forces are coplanar. Right, and this was just a look at how we approach such problems. Right, so next we are going to look at problems that are acting on the same plane, so coplanar, as well as acting on the same point at the same time. So coplanar, concurrent forces. Right, see you on the next one.